All right, doing our examples here for our vector valued functions. This is just doing parametric equations in a vector form is really all it is. So here, example 1, it says this is our vector, 1 plus t cubed, comma, t times e to the negative t, comma, sine of 2t. So the first thing, part A says find the derivative. So for part A, we want r prime of t. So that's just going to be a new vector whose 3 parts here, because this is a 3-part, so this is a 3-dimensional one. We're just doing the derivative of each piece. So the derivative of 1 plus t cubed is going to be 3t squared. So that's the answer to the first one. And then we need to do the derivative of the second part. So this is t e to the negative t. This is a product, so I need to do product rule here. So it's going to be first function times the derivative of the second function. So that would be e to the negative t times negative 1 plus the second function, e to the negative t times the derivative of the first one, which is going to be 1. So I just had to do product rule. Now the derivative of sine of 2t, the derivative of sine is cosine. I keep my angle 2t the same, and then I chain on the derivative of 2t, which is 2. And then I put the ending. So there's my derivative. Not hard at all. All right. So part B says find the unit vector, the unit tangent vector at the point where t equals 0. All right. So our unit tangent vector at the point where t equals 0. So, well, this is your tangent vector right here. So we just want to make this a unit vector at t equals 0. So first of all, let's find the tangent vector that we're looking for. All right. So at t equals 0, I'm plugging in a 0 for all of these. So this would be 0. So plug in a 0 for these guys, that would be 0. Plug in a 0 for this, e to the 0 would be a 1. And then plug a 0 in for this one. The cosine of 0 is 1. 1 times 2 is 2. So there is my tangent vector at the point where t is 0. And I could have put a 0, I guess, right there. T of 0 equals 0. All right. Now I want to make this a unit tangent vector. Well, to do that, you got to divide it by its length in order to make it have 1 unit length. Right now, this has a different length. So its length is going to be the square root of 0 squared plus 1 squared plus 2 squared. So that's going to be its length. So its length is the square root of 5. So if I divide this vector by its length, the square root of 5, I've made it a unit vector. So t sub 0, t of 0 divided by square root of 5. I'm just going to divide these values by square root of 5. So now this is a unit vector, a unit tangent vector. So the tangent vector comes from taking the derivative, right? Because the derivative is where you get your tangency, all right, when we do our tangent lines. And then to make it a unit vector, I had to make its length a length of 1 unit. So they said do the tangent vector at t equals 0. So I found the vector for t equals 0. I found its length. I divided that vector by its length, and that means now this is a unit vector. All right. So this is a unit tangent vector now, and that's all there is to it. Nothing big there. Okay. That's probably the only new thing we're going to talk about is doing a unit tangent vector. Everything else is pretty much the same old hat that we've been doing with parametric equations. All right, for the curve, r of t equals square root of t, comma, 2 minus t, there's our vector. Find r prime of t. Then find the position vector r of 1, which all that means is plug 1 in here. And then find the tangent vector r prime of 1. So once I find the derivative, I'm just plugging 1 into that. All right, so I'm told that this is r of t. So let's find r prime of t. So r prime of t is going to be the vector where I just take the derivative of this. All right, so the derivative of this is t to the 1/2, so that's going to be 1/2 t to the negative 1/2, taking his derivative. And then the derivative of 2 minus t is negative 1. All right. If I want to rewrite that to where it looks a little better, I can write this as 1 over 2 square root of t, just rewriting t to the -1/2, putting the denominator, comma -1. All right, so there's my first part. There's my r prime of t. That's just taking the derivative of the x function and the derivative of the y function. That's all it is. All right, now find the position vector r1. Well, r of 1 just means plug a 1 into this r here that they gave me, this vector. So that'd be the square root of 1, which is 1. Then plug a 1 in here. 2 minus 1 is 1. So all I'm doing for r of 1 is just plugging 1 in for t into the vector they gave me. That's my position vector when r1. Not a problem there. When t is 1, that's the position. I'm at 1, 1. All right, then let's do the tangent vector r prime of 1. Well, I found r prime. So now r prime of 1 just means you're going to plug a 1 into your derivatives here that you got. So if you plug a 1 in here, that's going to be, and remember, we're just doing vectors, so I just have to put it in a vector format. So I'll put a 1 in for t. I got 1/2, and then that's just still -1. That doesn't change. All right, it's that simple. So you're just taking the derivatives of the functions in the vector format, and then you're just plugging in the value t is 1. That's all you're doing. Okay, problem 3. If a particle moves in the xy plane, so we're in 2 dimensions, so that at time t greater than or equals 0, its position vector is this, then at time t equal 1, its velocity vector is going to be what? Okay? Common sense, right? This is our position vector. We already know the derivative of position is velocity, right? So that means my velocity vector, v of t, is going to be the derivative of this guy they gave me. So the derivative of t cubed minus 1 is 3t squared. The derivative of the natural log of this business, all right, that's going to be, remember natural log, I can multiply the 1/2. Let's see, I'm going to do a little scratch work on this one. All right, natural log of the square root of t squared plus 1. I'm going to write that as the natural log of t squared plus 1 to the 1/2. I'm going to use the power rule, or a logarithm rule, and multiply my power to the front. So 1/2 ln of t squared plus 1. All right, so now I'm going to take the derivative of this. So the derivative would be 1/2, keep my coefficient. The derivative of natural log member is the derivative of the function, so 2t, divided by the function. So now this 1/2 cancels that 2. So my answer is t divided by t squared plus 1. Okay, so I did a little scratch work because I didn't want to do the derivative of a radical. So I would rather rewrite the natural log as this expression raised to the 1/2 to where I could toss the 1/2 to the front. So it makes doing your derivative a lot easier. All right, so that derivative ended up being t divided by t squared plus 1. All right, so that's my velocity vector. So it says at time t equals 1, what is my velocity vector? So I'm doing v of 1. So now all I'm doing is plugging a 1 in here. So I've got 3 comma, plug a 1 in here, will give me 1/2. So there's my velocity vector when t is 1. So remember, velocity is the derivative of position. So all you have to do is take the derivative of the position vector, take the derivative of its pieces. That's all it is. I mean, we're not overthinking this. All right. So if I was to graph, let me just mention, if I was to graph this, this would be a vector that starts at the origin and goes to the point 3 comma half is what that would be. All right, that's the velocity. It tells you the direction you're going and all that. All right. So now, a particle moves in the xy plane so that at time t, its position vector is this. So this is our position vector this time. At time t equal 2, what's its acceleration vector? Well, we know how to do that. Well, our velocity vector is going to be the derivative of the position vector. So that's going to be 3t squared minus 2t for the first component. And then the second component, that derivative is going to be 1 plus derivative of ln of t will be 1 over t. All right, that's our velocity. Now to find acceleration vector, we're going to take the derivative again. So the derivative of this first component is going to be 6t minus 2. The derivative of this component, derivative of 1 is 0, And the derivative of 1 over t, that's really t to the negative 1. So that's going to be negative 1 t to the negative 2. So that's 1 over t squared. Negative 1 over t squared. All right, so all I did was take the derivative of 1 over t. So now it says at time t equal 2, what's the acceleration going to be? The acceleration vector. So now I'm doing a of 2. So I'm just plugging a 2 in here. 6 times 2 is 12, minus 2 is 10. Putting a 2 in here, 2 squared is 4, so that's going to be negative 1/4. So there we go. There's our acceleration vector when t is 2. 10 comma negative 1/4. Easy, easy, easy. All right, number 5, a particle moves in the xy plane. That just means we're in 2 dimensions. So that at time t, its velocity vector is this. So this is our velocity vector. Find the position vector. Okay, if at time t equals 0, the particle was at 3, 2. All right, now we know if we've got the velocity vector, how do we find position vector? We integrate, okay? So our position vector, r of t, because this is already v of t, this is our velocity vector. Our position vector, which is called r of t, all right, is going to be the integral of these guys. So this will be the integral of 2t and the integral of cosine t dt. All right, so what will that be for r of t? So what is the antiderivative of 2t? Well, that's t squared. And then we got to add that plus c. All right, then over here, what's the antiderivative of cosine? Well, that's sine. And then you got to add that plus c. So you may want to call these c sub 1 and c sub 2 because those are not going to be the same c's. All right, so now we use the rest of this information to figure out what the c values are, okay, because we're wanting to find the position vector. So we're not done finding the position vector until we find these constants. So that's why they told us at time t equals 0, the particle was at the point 3, 2. So that means for this function here, t squared plus c equaled 3 when the time was 0. So when 0 squared plus c, we equaled 3. So that means c is 3. So I know c is 3, so that means that expression is t squared plus 3. All right, over here, I know that at time t equals 0, so sine of 0 plus c sub 2, our position was 2. Okay, so I know the sine of 0 is 0, so that means c sub 2 is 2. So I now know that this expression, sine of t plus 2, this is my position vector. So my position vector is t squared plus 3 sine of t plus 2. Because at t equals 0, that puts me at the point 3, 2. I also know that if I take the derivative of this vector, I'm going to get 2t and the cosine of t. So taking the derivative and putting in time t equals 0 gives me all of this information they gave me in the problem back. So this is the correct answer for the position vector. So all we had to do was integrate each piece and use the t equals 0. This is the position. So this is the first coordinate. This is the second coordinate. You just have to make them match up with the coordinates, the components within the vector. That's all it is. Easy, easy, easy. All right, last problem, number 6. A particle moves in the xy plane. That just means we're in 2 dimensions again. So that at time t, its position vector is this. All right, it says, well, what value of t is the particle at rest? All right, well, just like we did when we've done other problems where we wanted to be at rest, when you're at rest, your velocity is 0, right? Your velocity is 0. So a particle moves the xy plane. We've got its position vector. This is the position vector. Well, how do you find the velocity vector? Well, the velocity vector is going to be the derivative. So let's do the derivative of this. Let's see. The derivative of that is going to be t squared, because 3 times a third goes away, t squared. Then this will be minus 5t plus 4. So there's the first component. And then the derivative of this is going to be 3t squared minus 3t, and then minus 36. So all I did was take the derivative, that gives me my velocity. Now, I want to know at what time t is the particle at rest. So if your particle is at rest, that means your velocity is 0, okay? But we have two components of velocity. So what we have to do is we have to make both of these components 0. So let's do t squared minus 5t plus 4. That has to equal 0. All right, because that's the first component of our velocity. And then here's the second component, 3t squared minus 3t minus 36. That has to equal 0 too, because we just have two parts to our velocity vector. There's two components to it. So we just set them both equal to 0 because your velocity has to be at 0 to be at rest, all right? So let's factor these and solve. So when we factor this, we get t and t. Factors of 4 are 4 and 1 to give us 5 in the middle. They both have to be negative to get a negative 5 in the middle. So when I solve this, I get t is 4 and t is 1. All right, then over here, doing the same thing. I'm going to divide through by 3 just to make our math easier. So when I divide through by 3, I'm going to get t squared minus t minus 12. So now I can factor a little easier with smaller numbers. T squared is t and t. Factors of 12, that would give me a 1 in the middle, or 4 and 3. I need more negatives, so I need a minus 4 and a positive 3. So solving this one, I'm getting 4 and negative 3. So it said for what value of t is the particle at rest? Well, to be at rest, it has to be the same t value that makes both components of your velocity vector 0. So when you look at your two answers here, t is 4 is common to both of them, so that's the answer. So when t is 4, both components of our velocity vector are 0, which means we are at rest. All right, so when t is 1, that means your y-coordinate is not at rest. And when over here, when the t is negative 3, that means our y-coordinate's at rest, but our x-coordinate is not at rest. Our x-coordinate is moving. All right, so in order to be at rest, both your x component and your y component both have to be at rest. So they both have to equal 0. So you're looking for the number that is common to both components set equal to 0 on the velocity vector. All right, so pretty simple, pretty simple. All right, so that is those 6 questions dealing with section 13.2. So now we're going to do the other section, which is a lot more acceleration and velocity, and we're going to do some speed and distance. All right, so that's the end of that example video.